No? What type of functional groups do you see?
Carboxylic acid, amides.
What?
Carboxylic acid, amides, and esters.
Carboxylic acid, amide, carboxamide, amide, however you want to say it. Ester, what type of ester? Mouthful, ester. And
Amine.
an amino group, and a benzene ring, and a couple other carbons, yes. Can you do R and S for each stereocenter? But you can tell this compound will exist as a Zwitter ion. Yes or no? Will this compound be soluble in sodium hydroxide? Or HCl? Variety of other questions, yeah? That compound is aspartame. Equal. I think I showed that in the organic one, yeah? Yeah. Any questions before we get started? We have 3 handouts, green, blue, and white. Look at the white handout. Question?
What is a Zwitter ion?
Good question. The Zwitter ion is a molecule that is net neutral, but it has both a positive and a minus. So, doubly charged, but it's net neutral. White handout. Nomenclature. How are we doing on nomenclature of acid derivatives? Any questions about nomenclature? In the nomenclature video, did I go over this little bit on the side here, on the next page? Let's turn to the side.
You went over it in class.
Went over this in class?
Mm-hmm.
Okay, we've already gone over this. Omega-3, omega-6. Yeah, okay, we did. Okay, green. We talked about reactivity of acid derivatives. Acid chloride's most reactive, and hydride next, ester, and then the amides are least reactive. We talked about why. With amides, the nitrogen is a strong donator by resonance. So this resonance structure contributes a good bit to the overall structure. And we also saw proof of that because the NMR of this compound, DMF, here you look at the methyls should be equivalent, but they're actually not because of this structure here contributing. These methyls are not equivalent. One is cis to the oxygen, one is trans to the oxygen, because there's double bond character between the C and the N. And so the NMR was evidence of resonance. I think we're ready to pick up here, interconversion of acid derivatives. Okay, we kind of have a rule or a statement here. You can only convert to a less reactive derivative. Acid chloride, the most reactive. Thus, you can actually convert to an anhydride, an ester, or an amide directly. And we will see that. On the other hand, if you have an ester, you're going to be only able to directly convert to the least reactive one, that is to an amide. You cannot convert an ester to, say, an acid chloride, because that would be going to a more direct reactive derivative. We're talking about directly. You can convert an ester indirectly to any of these. I'm talking directly, and we will see what we mean as we go forward. What about an amide? Which of these can you convert an amide to directly? None of them. Because you can only convert to a less reactive derivative. And there's no derivative that's less reactive than an amide. I'm not including nitriles. I'm only looking at right now those with carbonyls. Okay? Acid chlorides are most reactive. It can be converted to many things. It's thus the most versatile. You cannot convert an amide to an acid chloride directly. If you did, you would say, well, maybe I need chloride anion. Okay? And maybe Cl minus could come in here, electrons up, back, and kick off the nitrogen eventually. It's not going to happen. Not going to happen. Why not? Why will this not happen? Well, first off, reactivity scale. This is not that electrophilic. Why? Because the nitrogen lone pair donates a good bit to the carbonyl, quenching any partial positive that may be here from this dipole. So we say this has low reactivity. Here, is that a strong nucleophile? It is an anion, but is it a strong nucleophile? No. That's a rather weak nucleophile, even though it's an anion. And we described in organic 1, we said strong anion, strong nucleophiles were anions. Yeah, but there's exceptions. Cl minus is not that strong. It's a pretty happy camper. That's why ACl is a strong acid. Okay? So you got a substrate that has low reactivity. It's not that electrophilic. And you got a nucleophile that's not that nucleophilic. So they just not going to have much reactivity here. Now, even if we could get it to these electrons to come in here and move electrons up, even if we could get to this tetrahedral intermediate, right? Tetrahedral intermediate we showed on the previous general mechanism. At this point, when electrons come back down and remake pi bond, because anytime you make pi bond kick off a leaving group, that's easy to do. What's it going to kick off, the Cl or the nitrogen? What's a better leaving group? Cl, halogen. And you end up with what? You end up with the same thing you started at the beginning, no reaction, no new product. So leaving group ability, the Cl is a better leaving group. And it's the worst nucleophile. So this is sort of the explanation of why you will not convert an amide to an acid chloride. Or it explains the statement above, which said you can only convert to a less reactive derivative. Compare this. You have an acid chloride. It's very reactive. Because not only do you have this, which all carbonyl acid derivatives have that, you also have this. And so this is going to make this a lot of partial plus. And so the nucleophile is very attracted here. High reactivity. And at this point, well, also be careful. I've lost an H. And so there's sort of multiple steps here. Taking care of the proton. Have we ever said that? We're going to have to take care of the proton here. But at this point, when this comes back down to form pi bond, which you're going to kick off? Cl or nitrogen? Cl. And so you end up with amide. So the acid chloride is converted to the amide. It's like kind of going downhill. So, in the end, what's our statement? Only convert to a less reactive derivative. And hopefully I explained to you why. The specific comments we made apply to anything up here. A general concept. We've already seen this in our mechanisms, but we already did a couple of mechanisms. For example, the Fischer Esterification, okay, which was the blue handout, yeah? Back in the first page. Fischer Esterification, we did mechanism. What was the first step in this mechanism? Protonate the carbonyl? Yes, we've actually already done it. So let's talk about that general concept. Protonation of the carbonyl makes it more electrophilic, more reactive. Actually, if you take an ester and just react it with water, or even heat it in water, trying to get an acid plus methanol, there'd be no reaction. But if you react it with water, and often this is heating, react it with water with an acid catalyst, we will get a reaction. And we already talked about this. This is the reverse of a Fischer esterification. So we've actually already talked about that. But the acid catalyst is important. Why? When we protonate the carbonyl, and make the oxygen of the carbonyl positive, it's now even more electron withdrawing. This oxygen now is like, hey, I really need electrons now. You made me mad. And it pulls on this pi bond more. We can even show resonance to illustrate this. It just takes the pi bond, move electrons up, and we can actually show a carbocation by resonance. So protonating the oxygen actually gives us more positive on the carbon. Now we can say a weak nucleophile, okay, this is a pretty weak nucleophile, neutral water, will add to the protonated carbonyl, nucleophilic addition. Now note, I'm adding to this resonance structure. These are the same. I could add the water right there. If water added to that carbocation right there, what would you get? You'd get that. And as I've always said, you can work with any resonance structure. Typically, we will always just sort of protonate and then add. But if you want, after you protonate, you can show the resonance structure. And then add. So, you can always work with any resonance structure. Either one of these will get you to this if you add water to it. Alright? But protonating the carbonyl makes it more reactive, particularly towards weak nucleophiles, which need, because otherwise they're not going to react. See? Water above. If there's no acid, it's not going to react. You're not going to get a hydrolysis reaction. But if you include the acid catalyst and protonate the carbonyl, it then will react. Protonation makes the carbonyl more reactive. Caution. Carbonyl is only protonated under acidic conditions, right? Strong acid. Not under neutral or basic conditions. Because under neutral or basic, you don't have strong acid. Why do I say caution? Because all the time, well, not all the time, because I will see you will protonate the carbonyl, but you won't be under acidic conditions. So you can only do it under acidic conditions, right? Okay. This general page includes all carbonyl functional groups. If there's a carbonyl there, you can protonate it. Esters, acids, amides. But it also will include aldehydes and ketones. Now that's test 4 chemistry. And when we get to test 4, we'll be protonating those carbonyls all the time. I'm just letting you know right now that this applies to aldehydes and ketones as well. Okay, there's a variety of miscellaneous things here. Let's get back to the blue. And did we finish up over here, C? Mixed anhydride, is that kind of where we ended on this handout? Chemistry of acid chlorides now. Is that where we're ready to start? I want to say one more thing on the green. One more thing about protonating carbonyl. Right here, protonating. This is an acid-base reaction. But that's the acid. This must be the base. Is this a strong base? I mean, anything that reacts with H plus is called a base, but do you consider this ester a base? Not really. Well, then how's it reacting? Well, let's look at the equilibrium, the numbers. Which side's favored here at equilibrium? It's a strong acid. Well, maybe we should not look at this. Because it's a little bit too convoluted. Here's the statement I'll make. This here is never isolated. Never isolated. On the other hand, if you take something like ammonia plus HCl, you will get both of these are gases. These will react to give you a new product, ammonium chloride. It's ionic. You can isolate it and say, hey, I have this product, ammonium chloride. Because it ain't one of these gases. I'm never going to come in here and say, hey, I've got a protonated carbonyl here. This is only going to be seen in mechanisms. It's terrible equilibrium, actually. Especially if you're in an aqueous environment. Because if you got water, which is a stronger base, water or the carbonyl? One. You seem confident in that. They're both oxygens. What's the difference? Hybridization. What's hybridization of the oxygen in water? sp3. What's the hybridization of oxygen in a carbonyl? sp2. Which one holds the electrons tighter? sp2. Carbonyl holds the lone pair tighter. This oxygen holds these lone pairs tighter than water. Water's a better base.
Is resonance also an explanation?
Do what?
Is resonance also be an explanation?
No. Resonance would actually be an argument for making it a stronger base, I think, because resonance depends on if you're talking about resonance of the neutral carbonyl or the protonated carbonyl. I think hybridization, let's don't get into that too much more. I think the statement I wanted to make is you're not going to isolate this because it's not a good equilibrium. We're just going to protonate in mechanisms. Okay? You're never going to make that salt. It's got to be a minus here, and so it would be a salt. Just like ammonium chloride is a salt. You're never going to make that salt. Hey, I made a protonated carbonyl salt. But very important in mechanisms. Okay, chemistry of acid chlorides. What can you do with them? Well, you can hydrolyze them. They will react with water. No acid catalyst needed. No H plus catalyst needed. We don't need to protonate this carbonyl. Acid chloride is very reactive. It's the most reactive of the acid derivatives. It will react with pure water. And these electrons will come in here, add the carbonyl, electrons up, Nucleophilic addition to carbonyl. What's next? Yeah, we can come back down and kick off the chlorine and we can get home. Which is a better leaving group, Cl or O protonated oxygen? They both can be leaving groups for SN2. How about if we take care of the proton first? At this point, you've got an oxygen minus. That looks like a base. You've got something that looks like H3O plus, an acid. How about a proton transfer? And let's put the H on that oxygen. And do this. That's just going from that Zwitter ion. What's a Zwitter ion?
Neutral, 2 charges.
Neutral molecule with, okay. Proton transfer, that looks like it wants an H+. This looks like it's wanting to give up an H+. Could do that. Now what do you want to do? To get home. Now, anytime you make a pi bond, now which is a better leaving group, Michael? Chlorine or OH? Now it's clear. If you go back to SN1, SN2 type stuff, leaving group, okay? This needs to be protonated to make it a good leaving group. Now both of these can leave because anytime you make a pi bond, either one can be kicked off. But you're always going to kick off the better one. And the better one here is clearly the chlorine, and when we kick it off, what do we get? Oxygen, OH, there's an H here. Yeah, everybody agree? And how do we get home? Well, there's a Cl minus. This can take the H, these electrons stay here, and we get neutral product plus HCl. Now, most books, and probably most instructors, will not show this H plus transfer. Most will probably just bring these back down and kick off the chlorine. And then you would have double bond here, and then the chlorine would take an H from here to form the HCl and go neutral. What did I do though? I took care of the proton. I said that a month ago, we got to take care of the proton. Okay? You often have to say, okay, let's deal with this proton. And again, when you get to biochemistry, it's going to be like, what happened to the proton? Well, they took care of it and they didn't even tell you about it. Okay? You can do these steps kind of differently. I took care of the proton. I did a proton transfer. Seems reasonable. I got a minus and a plus. Let's transfer the proton to there and get this. Okay? Caution. Second caution today. Bottles of acid chloride usually give off HCl gas when open. Well, I've got an acid chloride here. I'll get it out. Whew. Acid HCl gas came out. I got to be careful. Why?
Water in the atmosphere?
You're going strong today. Water in the atmosphere.
So it's so reactive, it would react with water in the atmosphere.
Yeah. No catalyst needed. Water in the atmosphere. It's been opened before. Water went in the humid air. It got in there, reacted. The cap was on. Then someone comes by a month or two later or whatnot, takes the cap off. Now the HCl comes out that it formed in this reaction. And your acid chloride also contains some acid. Very often when you use an acid chloride, if it's old, if it's been sitting on the shelf for 6 months or 5 years, before you use it, you'll distill it to get rid of the carboxylic acid that's in there. Acid chlorides tend to be reactive intermediates. Just sitting on the shelf in the humid southern air, once you open it up, okay? But also in nature, you're not going to find an acid chloride in nature because guess what? It rains in nature. Okay? So you're not going to find an acid chloride in a natural product. All right? Old bottles of some liquid acid chlorides, such as benzoyl chloride, often have a solid in them. Here's my liquid acid chloride. What's this solid at the bottom? I can't hear you.
The salt.
It's not a salt. No. This is a liquid. If the acid is a solid, and it's forming as it sits there, it could actually separate from the liquid. The liquid's my acid chloride, but I got some acid in there now because somebody left the cap off one day, and or basically the acid as it's formed as an impurity will separate as a solid. You're like, well, what's that solid? Well, it's the acid that is formed by hydrolysis. Okay, we can react this with methanol. Same thing, except the oxygen is going to have a methyl on it. And so instead of giving it carboxylic acid, we get what? Ester plus HCl. Now this is actually a reaction because you're not typically going to have methanol in the air. Okay. This can happen by accident from humid air. But this is a reaction we can do in lab if you want to make an ester. It's actually the second way to make an ester. The first was Fischer Esterification from a carboxylic acid. But now we see an acid chloride can be converted to an ester just by reacting with an alcohol. You do not need an acid catalyst again. Of course, you can also use the anions. Instead of water, what about KOH? Well, why not? Hydroxide, here, electrons up. Are y'all ready for a shortcut? You can't do this on a test, but I'm going to do it on the board to save ink and time. Electrons up. After electrons come up, what happens? Electrons come up,
They come back down.
they come back down and kick off the chlorine. And what does that give? Gives that. But we're under basic conditions. What's going to happen to our product? The base is going to react with the acid product. So what's the H plus workup for? These electrons react with H plus, and that's how we get the ultimate product. Reaction with amines. If you take an acid chloride reacting with amine, the simplest being ammonia, these electrons add to carbonyl, electrons up. Nucleophilic addition to carbonyl. What do you want to do next? Proton transfer, again, most books will not do that. Most instructors will not do it. Most will just come back down and kick off the chlorine. All right? I'm going to do proton transfer. Give that. Now that's a totally neutral product. Is this final product? Why not? I mean, everything's neutral. What, that could not be a final product? Why not that as final product? Because anytime you can make a pi bond with a lone pair and kick off a leaving group, that's very easy to do. This thing is going to lose HCl. How would we get product plus HCl? Yes, but we would make HCl, and that's going to be a problem. Why is that a problem here in this reaction? It wasn't a problem in the above reactions. Why is it a problem here? No. Is that a basic nitrogen? No. But there is a basic nitrogen up here. Ammonia is basic. If we generate HCl, what's it going to do to the ammonia? Ammonia will react with the HCl. Really, ammonia will take that H instead of that, and you'll have ammonium chloride. That's a problem. Thus, we would typically need like 2 equivalents of ammonia. And if we have 2 equivalents, what's going to take this H? The next equivalent of ammonia takes the H, stay behind, and we get product plus what? Not HCl, but ammonium chloride. And when I draw that, hopefully you know it's NH4 plus Cl minus. So one equivalent of the amine to react with the acid chloride, the other equivalent to take the HCl. If you only use one equivalent of ammonia, your maximum yield will only be 50%. Because half of the equivalent will react here to give you your 50% theoretical yield. The other half of your ammonia will react with the HCl that's formed. Now, I used ammonia here. You can use a primary amine or a secondary amine. You actually cannot use a tertiary amine. Because if we use a tertiary amine, there would be no H to lose. Because if there were 3 R groups on the nitrogen, 3 R groups would be a tertiary amine. You would not have an H to lose. So, benzoyl, I want you to know this name here, because that is a benzoyl group. And thus that is called benzoyl chloride. Product of benzoyl chloride reacting with methylamine, 2 equivalents of methylamine. That would be, I'll just draw the benzene as a phenyl. We would get that secondary amide. Mechanism for this reaction. Name of the mechanism? Nucleophilic acyl substitution. But we also have to take care of the proton, right? At some point, dealing with the proton. The one below the methyl carbonyl is, they call it, an acetyl group. And so that's called acetyl chloride. Some people say acetyl, some people also say what? Acetyl. Acetyl chloride, acetyl chloride, both are kind of common. In this reaction, I've got the amine on the, sort of over here, and the acid chloride on the reaction area. Where up here I had the acid chloride here and the amine on the line. Does it matter? No. They're both in the same flask. Does not matter. A lot of times you draw the smaller one on the arrow. Here this is the smaller thing and this is larger. That's the only consideration. Up here, this was the larger molecule, and that was sort of smaller. All right? Both cases, you've got an acid chloride and an amine. Now down here, instead of using 2 equivalents, we could do number 2. Here, we have an amine, but we did not use 2 equivalents. Instead, we added a different amine to act as the base, triethylamine. And triethylamine would be a nitrogen with 3 ethyls. It's a tertiary amine which will not react to give an amide. There are lots of this is sort of a sacrificial base. There's a variety of sacrificial bases that can be used. In the 8-week lab, what is a base that it was used? or can be used. Some of you have already used one. Dapco. Hasn't somebody used Dapco? Other one was 2,6-lutidine. Both of those are sacrificial bases, just like analogous to triethylamine. Because up here it's okay to use two equivalents of methylamine because it's cheap, easy to get rid of, very small molecule. Down here, what if it took you like the 6 months to make this? Do you want to use two equivalents with one equivalent just acting as a base? No, half of your molecule going in the waste container after it acts as a base, you don't want to do that. So let's use a cheaper base instead. Product here. This nitrogen is what? Now bonded to what? Carbonyl with a methyl. There is an H there. Yeah? Under my hand used to be what over here? Chlorine. But now it's what? The nitrogen nucleophile. What type of functional group did we make? Amide. But what type of amide specifically? The what? Acet. Call it an acetamide. Because the nitrogen has that acetyl group, the CH3 carbonyl. Use of acetyl chloride would give an acetamide. What type of amide did we make above here? We didn't. We used benzoyl chloride. What type of amide did we make? I'll write it up here. The one we made up there was a benzamide. This was called an acetamide. And if we did not use triethylamine, we would have made the acetamide plus what? HCl. What's the purpose of the triethylamine? To react with the HCl. So this will not. Questions? Why are acid chlorides key intermediates for acylation as opposed to the carboxylic acid? We can point this out. This is a general thing that we'll refer to as we move forward. If you take a carboxylic acid with a strong nucleophile, including something like a Grignard reagent, or an amine, which we just reacted with amines, I'll just use an amine, like ammonia. Will this add to carbonyl? No. What will it do instead? It will take the H. Carboxylic acid has an acidic proton. What about down here? Does the acid chloride have an acidic proton? No. So it will add to the carbonyl. This makes acid chlorides much better for reaction with strong nucleophiles. Because a strong nucleophile typically is also a strong base. Okay? We'll pick up here on Wednesday. Have a good day, guys.